going to move on to speaking about more of the mechanics of skeletal muscle contraction. So we talked about, the anatomy, the structure of the sarcomere. We talked a little bit about the processes, so the biochemical mechanisms that actually bring about the shortening of the sarcomere. And now we're going to get into the mechanics of how force is generated. So what are the factors that determines how much force a muscle can generate? We'll talk about things like the recruiting principle and the velocity of shortening. Okay, so we looked at the structure, and just to recap here, to start off with recapping, we looked at the structure of the sarcomere. We know that it's these thin and thick filaments. The active cross-bridge cycling is what we said generates the force for muscles to do work. And so we talked a lot about how that force is generated, how those cross-bridge cycles happen. Now we're going to talk about some factors that can change within the cross-bridge cycling that can determine how much tension or how much force is produced by different muscles throughout the body. So essentially, the type or the amount of muscle contraction depends on two factors: the tension produced by a single muscle fiber, and that is determined by the number of active cross-bridge cycles or cross-bridging that's happening, essentially how much actin and myosin interactions are existing in that muscle, as well as the number of that muscle fibers that's in a muscle itself. So a couple of factors will determine how much force that muscle is going to generate. So the more cross-bridge cycling that we have, the more force that muscle is going to generate. And then the second factor here is how many fibers are in that muscle contracting. Now, we've been talking about all of the sarcomere shortening, the entire muscle shortening, but we want to understand that in muscle, not all the fibers are always contracting at the same time. We're going to talk about the recruiting principle and how we can start out with a few fibers contracting, and then we can recruit more fibers if more force is needed. And so the two factors that will determine how much force a muscle generates is the tension produced by a single fiber and the number of fibers that are actively contracting. And so something else that we want to think about is the frequency of stimulation, because we spoke about this idea that if we increase the frequency of action potentials, we can increase the stimulation to muscle, and that will increase the amount of force. So there are two mechanisms or two ways by which we can increase the frequency of stimulating muscle. The first one is called TREP or TREP-A. And TREP is not really understood. So we don't quite know why muscle behaves this way, but we do know that if we stimulate the muscle once, right? So here's an initial action potential. It will generate some amount of force, not necessarily its maximum amount of force, but some amount of force. It will completely relax in between. If we stimulate it again, so a second action potential arriving here, it will generate more force. Okay, and if we stimulate it again and again, it will continue to increase the amount of force generated until it plateaus at its maximum force generation, which is standard for each muscle. And so again, the reason we don't quite understand TREP is because the muscle completely relaxes in between each of these contractions. We'll talk about summation here in a bit, but summation, the muscle does not relax in between. And so TREP is this increase in force generation or tension production that happens after subsequent stimuli are sent to this muscle, where each stimulus is preceded by a full muscle relaxation. So in between each of these contractions, the muscle fully relaxes, and then for some reason, when it's stimulated again, the amount of force generation goes up. So that's TREP, which is one mechanism of increasing the frequency of stimulation. The second mechanism is summation, and summation happens, we'll talk about why it happens in a bit, but it's basically when we stimulate a muscle and then the muscle does not fully relax in between each of those action potentials, in between each of those contractions. And so the next time we stimulate it, if we think back to the biochemistry here, we've got calcium in the sarcoplasm interacting with troponin. And so if all of that calcium does not leave the sarcoplasm back into the SR, then the next time we stimulate that muscle, it's going to be even easier to contract. It's going to be easier to generate more force because we already have some existing calcium lingering in the sarcoplasm. And now the reason that we have summation is because we can add these stimuli together. If we look at the length of muscle contraction, anywhere from 10 to 200 milliseconds, so quite a long period of time when compared to an action potential, for example. So an action potential is anywhere from 1 to 2 milliseconds, and muscle can contract much longer than that. So there's opportunity for another action potential to arrive on that muscle. And so we can start to add or overlap those action potentials, and likewise start to add or overlap those muscle contractions as well. And so this is the basis for why summation happens, right? The time period between the time it takes for a muscle to, remember, we talked about those phases of that twitch. So we've got the latent period, we've got the contraction phase, we've got the relaxation phase, and the time it takes for all of that to happen, we can then, simultaneously stimulate this muscle again and again, firing additional action potentials and, inciting more contractions that can then overlap in some. So let's look at an example here comparing summation to something that we call tetanus, and I'll explain what tetanus is in a bit. So if we stimulate muscle once, right, this is a standard twitch. We get that latent period where the machinery is warming up, calcium is moving from the SR out into the sarcoplasm, interacting with troponin. And all that we said takes time. And then we start generating force, right? The tension is going up here. And then we relax fully. So that's a single standard twitch. Now, if you look at summation, we excite this muscle, and before it can completely relax, we send another action potential, which stimulates it again. And so we're not starting from zero tension here. We're starting kind of at the midpoint. And so now we're going to go even further, right? So now that we're starting with a sarcoplasm that has calcium already in it, it doesn't take as long for that machinery to warm up the second time. And so when we, stimulate another action potential here, we generate even more force and even more force until we get to the maximum force or the maximum tension that the specific muscle can generate. And so we know why summation happens, right? Because the muscle isn't fully relaxing here, and we can explain that, the calcium that's already in the sarcoplasm. The reason this differs from trap, which I talked about earlier, is trap, we see full relaxation in between these contractions, but then the next contraction is somehow stronger. And that's kind of the difference between summation and trap, and why we don't fully understand or are able to explain the mechanisms behind trap, but we can for summation, okay? Now, if we would continually increase the frequency or how fast we're, sending these action potentials further, we would then get into what's called tetanus. And tetanus is really, this repeated stimulation of muscle that causes muscle spasm, which I'll talk about here in a bit. But essentially, if we continue to increase how fast those action potentials are being fired, then the contractions will start to just kind of overlap and jump on each other and sum together into one large contraction. So we will start out with incomplete tetanus, which is unfused. And so there's a slight bit of relaxation happening in between, but the amount of force is at its maximum. So the force generation will not go any higher here, but it's going to stay constant. And then we'll eventually get into complete tetanus, which is basically fusion of all those contractions into one large sustained contraction, which is called complete tetanus or fused tetanus, okay? And here we can see there's absolutely no muscle contraction in between. And kind of explaining again the biochemistry here, this is where all of the troponin is maxed out. So all of the troponin in that muscle has calcium bound to it. The maximum amount of cross-bridge cycling that's possible for this muscle is already taking place. And so no matter how fast we would start, we would increase the frequency of that action potential arriving on the muscle, there's no way we could generate any more force. And we would not even be able to relax in between those contractions. We just have this one, large sustained contraction here. And so just kind of reiterating here the cause of summation and tetanus. And on a bit of a tangent here, tetanus is where we get the word tetanus. If you've heard about the tetanus toxin or, the tetanus, infection, which is actually a bacterial toxin that affects our nerves. And it actually inhibits GABA. If you remember, GABA was a neurotransmitter that was inhibitory in the nervous system. And so it kind of provided some balance in the nervous system signaling. And so when we inhibit GABA, we overstimulate the nervous system. And this is what causes the spasms that we see with that tetanus infection. And so the word tetanus is really derived from this action, which is the overstimulation of muscle. Although these are two different ideas here. So tetanus, the muscle phenomenon, and tetanus, the actual infection and the way that it presents. So that's just a bit of a tangent there. So if you think about the cause of summation and tetanus here, again, it's happening because all of the calcium is bound to troponin. All of the troponin, rather, has calcium bound to it. And so we're providing the most tension that we possibly can. All of the possible cross-bridge, interactions are, happening. And so this is where the amount of calcium in the sarcoplasm is exceeding how much is being reuptaken back into the sarcoplasmic reticulum. And so here the calcium is increased in the cytosol. This will eventually max out our cross-bridge cycling and lead to a condition that's called maximum tetanic contraction, which can be fatal, right? Maximum tetanic contraction is sometimes an adverse effect to certain medications that we give. And basically it's where we have this complete spasming of the entire body, all the muscles in the body, and eventually they're all going to just give out. And this is how it can become fatal. If it affects the respiratory muscles, it could affect ventilation and breathing. And so maximum tetanic contraction will be the end point of increasing the frequency of action potentials. And at that point, the muscle will completely give out beyond that maximum tetanic state. Okay. All right. Let me pause here and see what questions you may have. So we've talked a little bit about that cross-bridge cycling and how it plays a role in the amount of force a muscle can generate. And then we talked a bit about how we can increase the frequency of action potentials in two ways. So trap and summation, and how we can eventually lead to the maximum force that a muscle can generate. Okay. Okay, so let's keep going here. So the next thing we'll talk about is the fiber diameter, because this is the second factor that we mentioned before. So just kind of bearing in mind those two large factors, or two large umbrella that we talked about at the beginning, that if we increase the amount of cross-bridge cycling, we'll increase the force. And if we increase the fiber diameter, we will also increase the force. So the force generating capacity of a muscle is the inherent amount of force that a muscle can generate. This is usually standard for different muscles. So for example, your gastrocnemius can generate a standard amount of force, your biceps brachii, and this will depend on how many cross bridges are in that specific sarcomere within that muscle. And again, that'll depend on, the shape of the muscle, the arrangement of those sarcomeres, but we want to understand more cross bridges per sarcomere equals more force, and then more sarcomeres in parallel equal more force. So not in series. We cannot influence how many thin or thick filaments are in a myofibril. We also cannot influence pretty much the length of that myofibril. So the amount of sarcomeres in series is constant. The amount of sarcomeres in parallel can be changed. This is increasing the amount of myofibrils in that muscle fiber, okay? And so the fiber diameter can vary by pretty much making new myofibrils. Remember, myofibrils are a subcellular organelle. And so a muscle fiber can make new myofibrils, which have more sarcomeres on them and are going to generate more force. And so a larger fiber diameter means that we've got more myofibrils jam-packed in those cells, because we cannot change the number of sarcomeres, the number of thin and thick filaments on a sarcomere. What we can do is add more myofibrils to increase the diameter of that muscle fiber. And so that's why we bulk up, we work out, go to the gym, the muscle fiber gets bigger. And what's happening is more myofibrils are being added into those muscle fibers. And so the diameter gets larger, and therefore the amount of force that can be generated also increases. So the statement at the bottom here says a larger diameter means that there are more filaments. I want you to make a note here, there are more myofibrils specifically, because we cannot change the number of thin and thick filaments, that's constant. What we can change is the number of myofibrils, which essentially has more thin and thick filaments on them, okay? And then that way we can generate more force. We also want to think about the fiber length. So that's essentially how stretched or contracted the muscle is. The length of the muscle fiber at the onset of the contraction really dictates how much force can be generated, because it dictates how much actin and myosin interaction can occur. And so muscles are typically at their resting length, which is an optimal length for them to be at to generate the maximum amount of force that can be generated for that specific muscle. And this is because of the amount of overlap, again, between thin and thick filaments. And so if we start out with a sarcomere that's really stretched out, not at its optimum length, the amount of overlap that we can produce is going to decrease, right? Because as we shorten that sarcomere, it's going to take more time to actually get cross-bridge cycling going. And so starting out with a really stretched sarcomere decreases the amount of force we can generate. Also, starting out with a really contracted or really shortened sarcomere will also decrease how much overlap we can produce and therefore how much force we can generate. Now in situ, and in situ here means the way that it is in the body. In situ, muscles are usually at their optimum length. That's why they're stretched across joints. So that's why muscles have an origin point and a point of insertion to keep them stretched at that perfect optimal length. And that is what allows them to generate the maximum force, again, for those specific muscles. So let's look at what happens when the muscle is not at its optimal length. So we can have a muscle that is greater than its optimum length, and we can have a muscle that is less than its optimum length. And let's kind of compare those two states here on this graph. So we're comparing the amount of tension as a percentage of the maximum tension for that muscle. And then we can compare the length again as a percentage of the resting length of that muscle. And if we look at a muscle that it's greater than its optimal length, right here out to the, the farthest end of the spectrum, we'll see that the sarcomere is really stretched out. And so when we start to shorten this sarcomere, the amount of actin and myosin interaction, or the amount of cross-bridge overlap that we're going to see, is going to be decreased because we're starting out with this really stretched out sarcomere. And so the amount of force we'll see is going to be less than the maximum force that that muscle can generate. As we shorten that sarcomere here, so slightly more shortened, but still quite stretched out, we'll see that the percentage of the maximum force increases. So we can now generate about 50% of the maximum force for this muscle, but it's still not 100% of the maximum because we're starting out with this sarcomere too stretched out compared to the optimal length. On the other end of the spectrum, if it's at less than its optimal length, we've got the thin filaments pretty much touching each other, as we can see here, this really shortened sarcomere to start. And so when here again, not going to see the maximum amount of cross-bridge overlap that we would see if the muscle started at a stretched length, not overstretched, but at its optimal length, where we would see the maximum amount of cross bridges for that muscle. And in this really contracted state, we'll also see that the Z lines are really close to the thick filament. So there's pretty much no room for sliding to happen. And so the force here is obviously not going to be as much as it would be when the muscle is up here at its optimal length, and the percent of the maximum force generated